Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. When a molecule contains both a hydroxyl group and a nearby tertiary carbocation stabilizing group, treatment with HBr can protonate one of to form a carbocation, which can then be trapped intramolecularly by the other of to form a cyclic ether, tetrahydropyrin, rather than being trapped by bromide. Moving on to the next step. The substrate is a 1,2-diol on a cyclohexane framework, where one O is a primary CH2O, unlabeled, and the other is a tertiary 18O on a carbon also bearing a cyclohexanyl group. The tertiary position is highly stabilized. Moving on to the next step. HBr protonates the tertiary 18O, the better leaving group, as it forms a more stable tertiary carbocation to give a tertiary carbocation with loss of H2-18O. And for the final step, the primary hydroxyl oxygen, unlabeled CH2O, acts as an intramolecular nucleophile and attacks the tertiary carbocation. This forms a 5 or 6-membered cyclic oxonium ion, which loses a proton to give a cyclic ether, tetrahydropyrin ring. The oxygen in the ring comes from the unlabeled O, and the 18O is lost as water. The product is a bicyclic compound where the oxygen bridge is formed from the unlabeled O, consistent with option A, which shows the cyclic ether with no 18O label on the ring oxygen. Option B shows the 18O in the ring, which would require the tertiary 18O to be the nucleophile and the primary O to leave, but primary carbocations are not stable. This pathway is disfavored. These show open-chain bromide products. In CCl4, nonpolar solvent, with an intramolecular oxygen nucleophile available, cyclization to the ether is faster than intermolecular bromide attack, especially when a favorable ring size results. The cyclic ether, tetrahydropyrin, 6-membered, is strongly preferred. The major product is the cyclic ether formed by loss of the tertiary 18O has water and cyclization of the unlabeled primary O onto the tertiary carbocation, giving the bicyclic tetrahydropyrin shown in option A. Therefore, the correct answer is A. Therefore, the correct answer is option A.